Hello, good evening, and welcome everybody to this very special Sigma meeting for May 2023. This meeting is for the George Fraser Memorial Lecture. For those of you who don't know me, my name is Pete Sherman. I'm the chairman of Sigma, and I'll be your MC for the evening. I would like to start by not just welcoming all our Sigma members to the meeting, but also all our affiliated club members. There's the likes of Highland Astronomical Society, Aberdeen Astronomical Society, Caithness Astronomical Group, North Ronaldsea, and the Cairngorm Astronomical Groups. And also, I believe we got a few people coming in tonight from Dundee Astronomy Society as well. So you're all very much welcome. I'd also like to welcome any visitors we have tonight here on Zoom, and those of you who are also joining us on YouTube this evening. Those of you on YouTube, please subscribe to the Sigma channel. And also don't forget to give us a like now and again. It all helps out, and it's really very much appreciated. Okay, on with the meeting. Tonight's meeting will run a little bit differently than usual. We won't be having a break or a second half. This is purely the meeting in memory of Professor George Fraser. In a few minutes, I shall be handing over to Dr. Howie Firth, who will give us some background on and information about George Fraser. And then he will be introducing tonight's speaker, Professor Nigel Bannister. But before that, I'll just explain how you can sort of ask questions and get involved in the meeting. If you're joining us on Zoom tonight, you can put your questions into the Q&A box. There's a little control panel that will pop up in your screen and you'll say Q&A on it. Just click that and you can put a question into there at any time throughout Nigel's talk. Chris is here, he'll look after that, and he'll ask his questions over to Nigel at the end of his presentation. We'll ask you not to put your questions into the chat box, because the chat can move very, very fast and the actual questions get lost in there and may not be asked. Okay. That chat is open at the moment, but it will be closed during the main talk because it does get a little bit distracting for our speakers if we keep getting pop-up bubbles coming up there. Okay, then. So if you have any issues at all, any issue with the stream or anything else you want to ask, there's a little raise hand button you'll see. You can click that, your little hand will go up, and one of us on the panel here will contact you through the chat to see what the issue is and try and resolve it the best we can for you. If you're joining us live on YouTube, obviously it's only for the live. If you're watching the repeat, you can try and put some questions in. We might be able to get them over to Nigel at a later date. But if you're live on YouTube at the moment, Rich Oakley is over there. You can put your questions into the YouTube chat, and Richard will then pass them on to Chris to be asked to Nigel in the same way as if you're on Zoom. Okay, so it gives me great pleasure to introduce to you Dr. Howie Firth once again. Many of you know Howie. He's been a Sigma member for many, many years, and he has helped Sigma out on many occasions in numerous ways. Howie Firth has directed Orkney Science Festival, one of the longest running anywhere outside of Edinburgh since its foundation in 1991. A mathematical physicist by training, he has had experience in teaching, broadcasting, writing, community development, and some spare time interest includes playing traditional music. Traditional Scottish music, I would say that is, or island music even. After graduating from Edinburgh University, where his teachers included Nicholas Kamer and Peter Higgs of the Higgs boson fame, he carried out postgraduate research at Durham University with Ewan Squires. He took a break from physics to become a travelling teacher in the smaller islands schools of his native Orkney. Interested in community development took him into broadcasting and a pioneering new type of community radio station, BBC Radio Orkney. In 1989, the City of Edinburgh gave him the responsibility of creating a science festival format, for which is now followed worldwide. He moved on to assist in other areas, and particularly Orkney, which has become known for its range and quality of participants. Awards include an honorary degree from the Open University, an award from the Institute of Physics, and an MBE for his service to popular science in the UK. He has lectured in 11 countries and written widely, and has particularly interest in the history and philosophy of science. I want to thank Howie for giving up his time tonight for doing this, and to introduce our speaker for the 5th George Fraser Memorial Lecture. Everyone, would you please welcome Howie Firth?
Oh, thanks for that. That was a very kind introduction, Pete. It's really an honor and a pleasure. Really, thank you very much. And Pete, I was just thinking, Sigma has great ability with the timing of this memorial lecture. I remember in 2017, it was on the exact date, 48 years on, of the lunar lander Eagle's liftoff from the moon. And today's timing coincides with the news of the first ground being broken at the site of the planned new spaceport in Sutherland.
Wow.
So Pete, you've timed this rather well.
I think it's more fortuitous and luck, I think, Howie, but we'll take it. I'll leave it to you. Okay.
Thanks, Pete. That new spaceport, in fact, will use rockets designed here in Murray by Orbex at their base near Forres and tested at Kinloss. And I was just thinking how pleased George Fraser would have been by the news. He was one of the visionaries, arguing from an early stage that a country with a big satellite industry needs its own launch facilities. He never forgot his old school motto from Elgin Academy, "Sic itur ad astra," thus we travel to the stars. And he committed his life to taking us that bit forward on the long journey into space. His hometown of Burghead is a place with sweeping views to a far horizon. And from Burghead and Elgin, he went on to Aberdeen University for a first-class honours degree in natural philosophy, the old Scots name for physics, and then south to Leicester University, where he would spend the rest of his working life as researcher, lecturer, professor, and then in 2002, director of the university's Space Research Centre. And his research skills were superb. He showed early signs of this in his PhD thesis on X-ray detectors. That thesis provided the technical foundation for the development of X-ray cameras for several international space astronomy missions in the years that followed. In fact, within months of arriving at the university, he was working on an X-ray camera for NASA's Einstein Observatory. Later, he worked on one of NASA's great observatories, Chandra. In his final months, he was working on the European Space Agency's Bepi-Colombo mission to the planet Mercury. He was in charge of the imaging X-ray spectrometer aboard, designing equipment to cope with the fire and fury of the approach towards the sun. The spacecraft has been swinging around the planet in huge flybys on course to enter orbit in December 2025. There are so many examples like this where George's work laid a foundation for the future. There are spin-off applications from his X-ray work in electronics and low-temperature physics, in medical imaging and archaeology. His work was recognized by awards such as the Royal Astronomical Society's Gwilt Jackson Medal, with a citation that said, "His contributions have played a major role in what has been recognized as a golden age of X-ray astronomy." And remarkably, and again confirming Sigma's remarkable skills of timing, just last week's issue of the magazine New Scientist carried a report of growing evidence for a particle called the axion as the origin of the mysterious dark matter that holds galaxies together. George would not have been surprised at this, as a paper that he wrote with several colleagues, published some months before his death in 2014, analysed a source of X-rays which suggested that they were being formed by axions coming from the core of the sun. So George will long be remembered for immense ability, combined with warmth, humility, and kindness. And when one day, far in the future, the great starships fly, I hope that one of them will be called the man from Burghead. The speaker for tonight's memorial lecture is someone who worked with him for many years. Professor Nigel Bannister arrived at the University of Leicester 30 years ago to take a degree in physics with astrophysics. He stayed on for a PhD, which involved him in the designing and building of a high-resolution extreme ultraviolet spectrograph flown in a suborbital sounding rocket from White Sands, New Mexico. In the years that have followed, Nigel's research has ranged from fundamental orbital mechanics to the use of spectroscopy for detecting cancer in the eye. Back in 2009, he began working on the mission to Jupiter and its moons, the mission that's called JUICE. And he was there in French Guiana just 3 weeks ago to see the launch of the Ariane 5 rocket that's making the long journey with a massive instrumentation aboard to study the giant planet and its 3 ocean-bearing moons. So he's the ideal speaker for tonight. And Nigel, welcome indeed.
Thank you very much, Harry. That's a fantastic introduction. And hello to everyone. I'm very sorry that I can't be there in person, but it's a real honor for me to be giving this talk in memory of George. George had a really major role in shaping my career. He was one of my 2 PhD supervisors, and later as the principal investigator of a project to fly an X-ray telescope on board the International Space Station. He appointed me as the instrument scientist. So that was my first postdoc position, was directly as a result of George. And although that didn't fly, it became the basis. The optical design was the sort of the forerunner of the instrument, which George guided and conceived, which is now flying, as Howie said, on board Bepi Colombo, now in the vicinity of Mercury. And I worked with George on many other projects. The work that I did in medical applications was really inspired by George's phenomenally diverse set of interests and ability to see links between the astrophysics and the instrumentation that he was developing, and apparently unconnected, unrelated concepts and problems in other fields. And that was a real inspiration. And my first academic position was as a direct result of George's guidance and tutorship, and I really credit George with setting me off on the career path that I'm now pursuing. So with that, I'm going to attempt to do what worked earlier and share my screen and my sound, and launch into my talk for this evening. And perhaps, Howie, could you just confirm that you can see my screen?
Yes, you're coming through loud and clear.
Excellent. Okay, thank you. So so my talk tonight is based on some work which I did for a TV documentary some years ago on the Apollo 13 flight, and looking at some of perhaps the lesser known aspects of that mission and some of the factors that led to its ultimately successful conclusion. Now, I have to be very clear about my sources and my role in this. So I can tell you succinctly that I had absolutely no role in Apollo 13 or any of that program. I was 2 days old on the. Oh, sorry, no. I was born 2 days after the first footprints on the moon. But I really credit the Apollo program as being the reason that I became interested and obsessed with astronomy and space flight, and I believe that that's why I'm working in the field now. So a lot of the work which I'm drawing on comes from a NASA engineer called Jerry Woodfill. Jerry unfortunately died last year, But he was one of the NASA engineers that was very close to the design and the operation of the Apollo architecture, and he did a lot of research on the Apollo 13 flight and some of the factors that led to its ultimately successful outcome, where successful means that the lives of the astronauts were saved. So I draw a lot on that, and also on the original Apollo mission reports, a lot of the ground loops that are available online. One of the really amazing things about NASA is their willingness and their ability to put enormous amounts of historical resource online for everybody to look at. So all of the materials that I'm going to show you tonight are based and are NASA sourced materials, and you can access them yourself. So the documentary that I worked on was called 13 Factors That Saved Apollo 13. It was part of a series of documentaries that I contributed to. It's still shown on various channels. It crops up occasionally on Discovery, and apparently I can speak fluent Italian, German, and French, although I don't ever recall learning those, as I've heard from colleagues overseas. So I'm going to be talking about some factors, perhaps some coincidences, some unintended events that contributed to the success of the mission ultimately. And I want to be clear that I'm not citing these as evidence of divine intervention or fate, not at all. I'm simply interested in looking at some of the aspects of the flight that may have contributed to the outcome that we know about. So this is a little bit like watching the movie Titanic. We all know how it's going to end, and so possibly 50% of you have now logged off. But for those of you who remain, the point here is to lift the lid on some of the lesser known aspects of the story. So, with that rather long preamble, let's begin by looking at the crew. So, on the left-hand side of the screen here, you can see the prime crew for the Apollo 13 mission. So, Lovell on the left, Ken Mattingly, who is the command module pilot, and Ed Hayes, who is the lunar module pilot. And the backup crew for the mission was made up by John Young, Jack Swigert, and Charlie Duke. So these two crews trained very closely together, trained extensively in the preparations for the flight, and the synchronization and the coordination was sufficiently tight that at any point in time, had one of the crew members had to be removed, then their counterpart on the backup team was ready instantly to take his place. And that indeed is what happened with Apollo 13. About 72 hours before the mission was due to launch, Ken Mattingly was pulled from the crew. And the reason for that was that he'd come into contact with Charlie Duke, the lunar module pilot in the backup crew. Charlie had caught measles from one of his children, and there was a major concern that if Mattingly had contracted measles, he would have been showing all of the signs of that infection, and with his performance being affected around the time that Lovell and Hayes were due to be walking on the surface of the moon. And so for that reason, at 72 hours before the launch, Mattingly's role was replaced by Jack Swigert. And that's quite an interesting choice, because Jack Swigert is one of the astronauts who had perhaps the most in-depth understanding of the command module architecture. In fact, Swigert was responsible for, or contributed to, a large number of the emergency and contingency procedures that NASA wrote into the mission plans for the Apollo program. So his knowledge of that system was unparalleled, and that undoubtedly provided a major advantage in the event that would have followed, because these events placed the astronauts under great strain. They had to think very rapidly, often through bad communication lines. And Swiggett's ability to recall this in-depth information was undoubtedly an advantage. So, to the objectives of the mission. So all of the Apollo missions were different. NASA didn't do anything twice. So the first Apollo missions, or the at least Apollo 11, landed on a region of the moon which was very, very close to the equatorial plane. And that site was chosen for two reasons. First of all, the equatorial plane was the only region that was accessible using the kind of trajectory that NASA had designed for that very first flight, a thing called a free return trajectory, which we'll look at shortly. So the equatorial region was where they were limited to. The Sea of Tranquility was chosen because, with the best high resolution imagery that was available at the time, that provided what appeared to be a very smooth landing area. And really, for that first landing attempt, it was about reducing risk, getting the astronauts down to the surface of the moon in a region where there was as little danger as possible of the lunar module colliding or toppling on rocks. And so a combination of factors led to Tranquility Base in the Sea of Tranquility on the lunar equator as being the chosen point. And of course, we know now that what looks like a very smooth terrain on that diagram on the left was anything but. And history records how Neil Armstrong had to take control of the lunar module manually to steer it over a boulder field that was exactly where they were intending to land. Nevertheless, of all the lunar regions, it's certainly one of the lesser challenging regions to go. The problem with this landing site is that, from a geology point of view, it's very limiting. And so, as the lunar missions became more and more advanced, NASA and the scientists who were involved in the project wanted to explore some of the other regions, some of the highland regions of the moon, which are available at higher latitudes. So this was the landing site that was selected for the Apollo 13 flight, the Frau Morrow lunar highlands, an area where there was potentially the opportunity to explore some of the ejecta, some of the materials that had been thrown out during the period in which the Imbrium Basin was formed about 3.85 billion years ago. So it was a real opportunity to investigate different lunar geology and to use a crater very close to the landing site, a crater called Cone Crater, as effectively a pre-made lunar excavation site where they could walk down into that crater and look at the strata and see and indeed sample rocks from different layers in the lunar surface and bring those back. And in the end, of course, Apollo 13 didn't make it there, but Apollo 14 did make it to the Frau Morrow highlands, and so those science objectives were ultimately achieved. So I wanted to say just a little bit about the trajectory. The trajectory that Apollo 13 took, which we'll look at in more detail later, differs quite a bit from the Apollo 11 trajectory. So Apollo 11 was labeled as the G mission. So the G mission was the first landing, and it took a particular trajectory called a free return trajectory. Now, the diagram that you see on the left here might be a little bit different to the ones that you see more commonly. Usually, you see this trajectory as a figure of 8. where the spacecraft leaves the Earth, loops around the moon, and then loops back to the Earth. In fact, this is exactly the same trajectory seen in a different reference frame. So what we're seeing here is the Earth at the center. The moon is seen orbiting around the Earth, and you'll notice that the spacecraft arrives at the moon on the ram side in the direction of the moon's motion around the Earth. Executes a series of orbits and then leaves on the wake side. So that is the figure of 8 profile. So this free return trajectory was a carefully designed trajectory, which meant that once the astronauts had fired the motor to leave Earth parking orbit, so the translunar insertion or injection maneuver, if they took their hands off and did absolutely nothing else, that spacecraft would travel to the moon, it would loop behind the moon, and it would come back to the Earth. It would re-enter the atmosphere at an appropriate angle and come back down into the ocean at a well-defined time where there was a retrieval vessel waiting. So it was a safety feature. It meant that the only thing that had to happen during the translunar injection was that the motor should burn for the period required to achieve that injection trajectory. And then, had they lost power, the spacecraft would have come back itself. There would have been other problems, but getting back to the Earth was not one of those problems. And the arrival at the moon involved the command module orbiting at an altitude of around about 69 miles, and then the lunar module would detach from the command module and descend to the surface. Now, in the case of the Apollo 12 missions onwards, this was not the profile. For the H-class missions, there was a deviation from that free return trajectory. There was a maneuver that took place midway between the Earth and the moon, which allowed the spacecraft to depart from that free return trajectory, and it allowed the spacecraft to access different latitudes on the moon and therefore to access more interesting landing sites. But of course, that introduced risk, because now the spacecraft would not automatically come back to the Earth in the event of a problem. There was another deviation from the Apollo 11 approach, which took place during the lunar orbit phase. So instead of orbiting at a constant circular altitude of 69 miles, the Apollo 13 flight was designed to drop down to a periapsis of about 9 miles, and that would allow the lunar module to burn less fuel in the descent and therefore have more fuel available for precise landing on the surface. So a very different kind of profile. Apollo 13 was the first mission to use the third stage, the S4B stage, as a method of doing science. So the Apollo 11 and 12 missions placed seismometers on the surface of the moon, and then later missions were designed to crash their upper stage motor from the final stage of the Saturn V, crash that into the moon, and they would use the seismic signature from that as a way of probing the subsurface regions of the moon. So part of that Apollo 13 stack did actually make it to the surface of the moon, but not all of the intended elements did so. So just, I'm not going to dwell on this. This is just to show you those are the classic free return figure of 8 here. And this plot comes from one of the Apollo mission reports. Here is the figure of 8 now shown to scale. So the loop around the moon is very tight. But the mid-course correction 2 is the one that departs from that free return trajectory. You can't see a lot of difference on this side. What you can see is that in this case, when the spacecraft loops around the moon, if there isn't another burn to return the spacecraft to the Earth bound leg, the spacecraft simply misses the Earth. So this was a big challenge, which we'll come to shortly. So
14, 13, 12, 11. commit, and we have liftoff at 2:13. The Saturn V moving to thrust, and it has cleared the tower.
This is Mission Control Houston. We appear to have a good first stage at this point.
Okay, so that was the launch, the sort of the classic Apollo era spectacular show of the Saturn V first stage, lifting that stack into the sky. That launch did not proceed quite according to plan. So at various points in this talk, I'm going to show you some transcripts from the flight log. But I appreciate that it may be difficult to see on your screen. So what I'm going to do is I'm going to play the audio from the ground loop archives that are available online. And the point that I want to highlight is a point sometime after the first stage was jettisoned and the second stage was lit. So what you've just seen is the power of that first stage, powered by the 5 F1 engines burning liquid oxygen and RP1s, a hydrocarbon. Effectively, it's kerosene. But later in the flight, that stage drops away, and the second stage, running 5 F1 engines, J2 engines, burning liquid oxygen and liquid hydrogen, take over. So at 2 minutes 48, you will hear the S2 ignition. So let's just start. This is the capsule side of the communication.
The clock is running. Okay, P11, Jim. Yaw program. Clear the tower. Yaw complete. Roll program. Houston, roger, roll.
So what you've just heard is the first few seconds as the spacecraft passes the tower, clears the tower. The spacecraft is rolling and yawing into a configuration that allows it to build up velocity in the required direction to ultimately to achieve orbit. At 2 minutes 48, we hear this is a few seconds after the jettison of the empty first stage. We hear the ignition of the S2, the stage 2 motors.
S2 ignition. Roger.
So that was exactly on schedule. But at 5 minutes 32, 2 minutes before the second stage burnout was scheduled, something else happens.
Inboard. Roger, we confirm inboard out. Houston, stand by for S4B to COI capability. S4B to COI, roger. Roger, you've got it now, Jim. We've got S4B to COI.
Okay, so I'll stop it there. So that inboard signal sounds innocuous enough, but it actually isn't. By the command module pilot giving the inboard signal, what he's actually saying is the inboard engine has shut down, and it shut down 2 minutes before it was due to shut down. Unfortunately, the amount of delta V, the power, if you like, that's available with the other 4 engines was enough to insert the spacecraft into orbit. That COI, by the way, is contingency orbit insertion. So that call, which you can see coming through at about 5 minutes and 50 seconds, is confirming that the spacecraft is capable of being now inserted into an orbit, so that in the event of an abort, the spacecraft or the astronauts are not going to be coming down back through the atmosphere. There's an opportunity to place the spacecraft into an orbit, a stable orbit around the Earth, to work a problem and select whatever abort mode contingency plans are appropriate. So there's a little bit of time went by. At 21 minutes 44, there's another conversation.
Apollo 13, Houston. Go ahead, Houston. Okay, a couple minutes to LOS, Jim. Everything is looking real good. Your AOS time at Carnarvon will be 52:36. And we don't have too much of a handle on why the inboard cut off early, except that it apparently was an engine problem and not a switch select function. But we're certain that you'll be able to make TLI based on what we're looking at now. Roger, nothing like an interesting launch. That's right.
So that's a rather interesting call. So that's the command center mission control confirming that the mission was good for translunar injection. So there was no fallout from that early engine shutdown. And Lovell's responding, Roger, there's nothing like an interesting launch, which sort of implies that that's the excitement over with. And of course, it was anything but. So what was going on there? What was going on there was a very impressive example of an effect called pogo. So pogo is something that has affected liquid propellant rockets since their inception. And it was a problem that really plagued the Moon program. At one point, there were 9,000 engineers within the program working on some aspect of this. So pogo is effectively, it's a resonance effect. So the construction of the rocket is such that you've got very high thrust coming through those engines. Above the engines, you've got a set of vertically aligned fuel lines, which are being fed fuel at a very high rate from the turbo pumps on board. And so this system has a resonant frequency. Any structure has a resonant frequency. The complication with this system is that resonant frequency is changing because the mass properties are changing as the rocket burns propellant. The mass of the system changes, and therefore the resonant frequencies change. And as the system is ascending through the atmosphere, the amount of disturbance that it feels from atmospheric effects also changes because the vehicle's getting faster and the atmospheric density is dropping. So and in particular circumstances, this can build up an oscillation because the engines are first of all fed a slightly higher rate of propellant during an oscillation in one direction, and then as the vehicle oscillates in the opposite direction, and this is taking place at several cycles a second, the propellant feed drops. There's not enough propellant to sustain the thrust, and the thrust drops off. So you get this what can be an extremely aggressive vibration. And in the case of the Apollo 6 uncrewed flight, that was so severe that it actually shook panels off the side of the rocket. So what happened during the Apollo 13 launch was a very severe example of pogo. You can see the situation here. So there are actually several different vehicles which are represented here. This is the Apollo 13 launch vehicle. These other ones are earlier flights, including Apollos 9 and 10. And it happens in a number of flights, and it happens cyclically. So the vibrations expand and then they diminish, and then there's another cycle and another cycle. What was unusual about Apollo 13 is that the expansion of these oscillations diverged very rapidly. And you can see that, in fact, in the next cycle, the oscillations are almost off the scale. So this is a 12G peak oscillation. And what happened in the flight to cause that engine shutdown was a low pressure warning that caused the center engine to shut down. That center engine was oscillating because it's suspended on a cross beam at the bottom of the second stage. So these engines are closer to the sidewalls. this engine is suspended on a crossbeam, and that is the engine that shut down. Had that not happened, the indications from these data sets are that in the next oscillation, that engine would have exceeded the structural limits that it was designed for, and led to a failure of the vehicle. So in the post-flight analysis in the cold light of day, that period, about 5 minutes into launch, may have been the closest that these astronauts came to complete catastrophe. So with that behind us, the mission proceeded relatively uneventfully. And by uneventfully, I think we have to remember, and accounts from the time, are quite well known, that Apollo 11 was front page news. Apollo 12 was sort of not front page so much, but merited some column inches. But by Apollo 13, moon landings were old news, and coverage was much less enthusiastic and widespread. So this is the final TV broadcast from the Apollo 13 mission. I'm showing it. I'm showing it not because there's anything particularly significant happening on board. It's the usual tour of the spacecraft, but this is the last footage that would come from that flight.
It took me 1 hour to shave.
So we'll skip to the end.
Okay, Jim, been a real good TV show. We think we ought to conclude it from here now. What do you think? Roger, sounds good. And this is the crew of Apollo 13. Wish everybody there a nice evening, and we're just about ready to close out our inspection of Aquarius and get back to a pleasant evening at Odyssey.
So that was the final transmission, and so now we come on to the real sort of core of the flight and the events which followed, and that is to consider the oxygen tanks. And I'm showing this picture because this is sometimes mistaken as a photo of the Apollo 13 flight, because we can see some exposed hardware in the side. In fact, this is not. This is an Apollo. I think this one is Apollo 15, and what you're seeing here is the science instrument bay, which was a later addition to the architecture. So this contains cameras and other instruments, and the astronauts towards the end of the mission would do an EVA, an extravehicular spacewalk, and retrieve those cameras. But this is not a picture of the damaged Apollo 13 module as it's sometimes mistaken for online. So the oxygen tanks were a key part of this architecture. So the service module sits behind the command module where the astronauts are living, and the service module contains a lot of equipment. And in one of the sectors, sector 4, it's the electrical power generating hardware. So there are 3 fuel cells in there that take hydrogen on one side, oxygen on the other, and they combine those components through some very clever membranes. And I'm just thinking on my feet, and I think I'm right in saying that the fuel cell, the physics and the chemistry of the fuel cell was a Scottish invention. I'm going to check that when I come back out, but I think that's the case. So the cells, below the cells, there are 2 oxygen tanks and hydrogen tanks. And those tanks, cryogenic tanks, are supplying oxygen to the fuel cells, but also the environmental control system. So the oxygen tanks have an interesting configuration. So this is a view inside that bay. So these are the fuel cells on the top. You can see the top of an oxygen tank here. Here is a better view of the oxygen tank, and here is the hydrogen tank. So that oxygen tank contains supercritical oxygen. It's a vacuum design. So there are 2 walls with insulation in between. And inside that tank was a temperature sensor a heater which helped to control the pressure inside the tank, and you want to increase the pressure slightly when you want to deliver oxygen to the subsystems. A thermostat and a fan. So there are fans inside here because what used to happen in this supercritical oxygen was that it would stratify. You get different temperature layers throughout the structure, and the way that the quantity, the capacitance gauge worked was, in order to work out the volume of propellant in that tank, or the volume of oxygen in the tank, it would do a capacitance measurement that was affected by temperature. And so the fans were there to try and unify the temperature inside the tank in order to get an accurate measurement of the quantity. So here's some nice pictures of tanks. These are in a museum in Kansas. This is the outer tank. You've got a little burst disc there. It's a pressure relief structure, and some fill lines and electrical connectors. So one of the misconceptions from I think from the Apollo 13 movie, which on the whole is a fantastic and very accurate movie, is the delay between, or the instant response between the command that you're about to hear to switch the fans on to get an accurate quantity reading, and the disaster that we know followed. So in this little sequence, I want to demonstrate how much time actually existed between those events by looking at the event log here and playing the recording from the actual flight. So we're going to turn it on now.
Okay, GNC, you got any configuration items here?
Negative, flight.
Capcom, looks like the last item we need here is a stir on the H2 and O2 at their convenience.
Okay.
Okay, so that stir is telling the astronauts that we need to take a reading to find out, to confirm how much oxygen, how much hydrogen we have in the tanks. So we're going to stir the tanks. So that's turn the heaters on, turn the fans on, mix the oxygen up, so we get a nice uniform temperature, and then we can get an accurate measure of the quantity.
We've got one more item for you when you get a chance. We'd like it to stir up your cryo tanks. In addition, I have a shaft and trunnion.
Okay.
For a look at the Comet Bennett if you need it.
Okay. Stand by.
So at 53:18, they turn on the fans in tank 1. And in 53:20, they now turn on the fans in tank 2. And nothing has happened.
Flight guidance.
Go guidance.
We finally got our Delta H update. Do you want to just read it up to the crew or uplink it?
Let's see now. Can we collapse dead bands and do all that good stuff if we uplink here?
This is just chatter preparing for the next set of instructions for the astronauts.
Through the disky, are they going to do it?
Stand by one.
Yeah, we haven't stabled out.
Keep an eye on this clock and listen to the telemetry at 53 seconds.
The time to do it is now, guidance.
Flight guidance.
Go guidance.
As long as he's in poo and don't reselect it, he can uplink it or enter it himself, or we can do it either. Doesn't matter.
So the first thing you can hear is noise on the channel. So at 53 seconds, there's a scratchy sound.
Okay, why don't you got to pass the data for the crew checklist anyway on board, don't you? Right. Don't you got a page update? Well, why don't we read it up to them, and that'll serve both purposes. All right. Both have them entered, as well as why don't you tell them what page you want it in the checklist. Okay. Flight, tell me. Go tell them. We show the LEM overhead hatch is closed and the heater current looks normal. Okay. 5 guidance. Go guidance. We've had a hardware restart. I don't know what it was. Okay. GNC, you want to look at it? See if you see any problems? Roger, we're copying it, Capcom. We see a hardware restart. Okay, GNC, you got any configuration items?
So I'm going to stop it there because you may have just heard in the background the famous call, Houston, we've got a problem. So that happened almost 2 minutes after that tank was switched on. So what was happening here? What led to this? So oxygen tank 2 on Apollo 13 was tank serial number 0008, and it was originally installed as a tank in the Apollo 10 spacecraft. There was nothing wrong with the tank, but there was an identification of the need to remove the shelf that held these tanks from the spacecraft to do some work on some of the other subsystems which were being found to cause electrical interference with the instrumentation. So in the clean room of the Space Center, there was a procedure which took place to remove the shelf and the tanks that it held from the spacecraft. And there was an error in the way that was done. They removed 10 bolts from the shelf and tried to winch the shelf out with a crane. What had not been spotted is that shelf was held down by 11 bolts. And so without noticing that this was still held down, they put more and more tension on the crane. The shelf pivoted up. It was driven, or the top of the oxygen tank was driven into the underside of the shelf above. And then the sling on the crane broke, and that shelf dropped down about 6 centimeters. There is speculation, because it's never been proved, that this event may have created a problem, perhaps a displaced line inside that tank that led to the ultimate failure of the tank. But I want to stress again, it's never been proved. It's a speculative suggestion. In any case, that tank was removed, and the Apollo 10 spacecraft received a replacement tank. The tank was tested, and it was later fitted onto a different spacecraft, and that was the spacecraft that went on to become the service module for Apollo 13. Once on board Apollo 13, there was another issue. Another error, and it's a systems engineering error that took place during a detanking test while the spacecraft was on the launch pad. So this is Apollo 13 on the launch pad. You can see the extended gantry here, which is a service gantry that was removed, long before the launch. And they were doing a pressure cycling test at the center to fill the tanks and then establish that the tanks could be emptied. And what they found was that during that test, the first tank emptied as expected, but the second tank did not. So there were a number of contingencies that were considered here, but the one that was ultimately chosen was to apply full power to the heaters inside the tank, which on the ground was 65 volts DC. In flight, it was a 28 volt supply that came from the fuel cells. And so they applied 6 amps, 65 volts DC for 6 hours in that system. Now, one of the other safety elements within the architecture was a set of thermostat relays that were set to open when the temperature inside the tank exceeded a safe limit, and that safe limit was around about 25 to 26 degrees centigrade. what hadn't been spotted is that at 65 volts DC, which the system ran on the ground, if the relays attempted to open in that mode at 65 volts DC, they welded shut. And so what transpires, and what's backed up by every aspect of the investigation, is that during this forced pressurized detanking procedure that took place at Kennedy, the interior of that tank rose to a temperature of about 500 degrees. And that was found to exceed the temperature at which the insulation in the wires inside the tank would fail. And so this is one of the root causes of the failure that you've just heard. So here are the closed relays. This is some results from a ground-based test at I think this was at NASA Marshall. So we can see that the Teflon insulation is when this happened. But it's quite funny. He said to me, he said, actually, I was out of the room when the actual event happened. He said, I went out for a coffee, and all I can tell you is that everything was working fine when I left the room, which is quite funny. So they were up at the University of Leicester with Carol Vorderman on the right hand side, filming a piece for a TV article on the Apollo 13 flight, and they came to us because they wanted to do a reproduction of the oxygen tank failure. So we did this in our School of Engineering. I'm not going to play the whole thing. This is colleague Dave Weston. There's a small bottle of liquid oxygen this is in fact liquid nitrogen, not liquid oxygen, because it was too dangerous to do it with oxygen. And what we've just done, or what we've had Jerry Griffin do, standing here, is flick on the power supply to warm that up, just replicating what was done on the mission. So I'm going to skip on because it took about 1 minute 50 seconds for the desired results to take place, but that's about the same time that it took on the spacecraft. So I'm now going to just skip. That's Carol getting excited. So that shows you that's a 500 milliliter bottle of liquid nitrogen, not oxygen, and that went off with quite a bang. It actually deformed some of the structure in that safety box. So what's remarkable about this is that the pressure that was built up by that explosion. Well, I have to be careful. It's not an explosion; it's a rupture. There was a small amount of burning, which was the insulation, the Teflon insulation, the wires, but the bulk of the oxygen in that tank did not ignite. So it was a rupture of a tank and the escape of oxygen at high pressure. It was not an explosion. But that rapid ejection of gas into the service module blew out the side panel. Had it not blown out the side panel, projections are that the pressure inside the service module could have reached a point double the pressure it would take to separate the command module from the service module. So the fact that panel was blown away actually contributed to reducing the impact of this accident. Had it remained intact, the service module may indeed have come apart from the command module. So one of the sort of the fortunate aspects of this was that in the time after that event, when the astronauts were trying to figure out what was going on, they tried to close the hatch between the command module and between the command module and the lunar module. Because they didn't know whether there was a leak, they didn't know where the issue was, so shutting the hatch was good practice. What they found was that they couldn't shut the hatch, Jim Lovell writes later that he thinks that was quite a fortunate thing, because it meant that later on, when they had to get into the lunar module quickly, they didn't have a very long, protracted process to reopen the hatch, because as you can see on the right-hand side, that hatch is actually quite complex. It's very secure. It has venting and multiple layers of latches that need to be opened in the right sequence in order for it to be operated. So this is a very busy plot, but it shows the initial sequence of events. And what the astronauts were seeing here was rapidly decreasing oxygen levels. They were seeing that on 2 of the 3 fuel cells, they were losing power rapidly. One of the fuel cells, which was fuel cell 2, was still operating. But several minutes into this event, the command was given to shut down that fuel cell. And the reason for that is that the fuel cell that they shut down deliberately, which was fuel cell number 2, was still generating power, because it was taking its power from a different tank. It was taking its power from a thing called the oxygen surge tank, which was located within the command module. And that surge tank had 2 functions. One function was to act almost like a capacitor, to absorb fluctuations in the delivery from the 2 main oxygen tanks. But it was also there to provide oxygen inside the command module during the final phases of the flight, when it was separated from the service module during re-entry. So if they'd not shut down that second fuel cell, the last remaining powered fuel cell, they would have run the risk of running out of oxygen for that critical re-entry phase. So I'm just going to pause here because I'm looking at the time. Could I ask one of the Sigma team just to remind me how much time I have left?
You can go as long as you want to, really, tonight. We've got no second half, so within reason.
Within reason. Thank you. Okay. I will try to accelerate.
It's very interesting. Carry on. We don't want to lose anything. So.
Okay, so thank you for that. So here is the status after the incident. So the astronauts are currently within the command module. The service module has lost all its oxygen. The fuel cells aren't generating power. They have no idea what's happened. They've heard a big bang. I should also mention that the first thing that you heard after we know that the tank failed was a kind of static on the line. And the reason that you hear static is because that oxygen tank failure it induced a very significant impulse into the spacecraft. The astronauts could really feel the thing shaking, and that shaking misaligned, caused the spacecraft pointing to change, and the high gain antenna, which was responsible for maintaining the comms link between the spacecraft and the ground, pointed away from the receive antennas on the ground. So effectively, they temporarily lost the signal, and that's why you get that noise. So, the other thing that is not clear is what damage has been caused to the exterior of the spacecraft, and critically, the service module propulsion system. So this big engine that was responsible for putting the spacecraft into lunar orbit, for example, they have no idea what condition that's in because they can't see outside. There's no capability to do an EVA to get outside. There is power, but the only power that's now available inside here is a battery, and that battery is absolutely critical to power the spacecraft during re-entry. So they're in a really, really bad position. The lunar module is docked to the command module, as you can see here, and the lunar module provided an opportunity to act as a lifeboat. The lunar module's guidance and navigation system could be used for aligning the vehicle. And there's a propulsion system, obviously built into the lunar module. There's the descent propulsion system, which, as we'll see shortly, wasn't designed for this kind of use, but had been considered and indeed had been tested in a circumstance that would provide some confidence that it could be used for this purpose. But there was very limited power available within the lunar module for any kind of activity. So if you look at Apollo flight plans, you'll see that they're full of different abort modes. You heard one of them earlier, which was the reference to the contingency orbit insertion. There were 2 abort modes for a problem taking place at this stage in the mission. One of them was the direct return mode. The other one is the circumlunar return mode. So they considered both of these. So the direct return mode was possible because, or it was possible up to about 61 hours after launch, and this accident had occurred before then. So even though they departed from the free return trajectory by this point, it was possible to bring them back by doing a very significant burn on that service module propulsion system, so the big main engine on the service module. That would change the velocity of the spacecraft by about 1.9 kilometers per second. They'd have to jettison the lunar module because that would reduce the velocity that they achieved. But it would bring them back to the Pacific Ocean at about 118 hours after launch, and that was by far the quickest way of getting them back. And it may have been the most logical way to get them back. But for one issue, and the issue was the uncertainty over what kind of damage this event had caused to the structures on the outside of the spacecraft, particularly that big service propulsion engine. And Gene Kranz, in his book, which is a fantastic read, he describes it, really evocatively, the sense of deep foreboding that he felt about the possibility of using that service propulsion system engine. Even though it would bring them back quicker, he was really concerned that damage had been caused to the engine, and they just didn't know what was going to happen when they turned it on. So the alternative abort mode that was considered was this one, the circumlunar return. This required a mid-course correction at about 61.5 hours, and that mid-course correction would return them to the free return trajectory that would bring them back to Earth. And it was a very small correction. It was 12 meters per second that would have to be done with the lunar module descent propulsion system. That's what DPS means. It would bring them down in the Indian Ocean at about 155 hours after launch. That was very tight. The calculation suggested that they would have about an hour left of consumables by the time they splashed down. But there was another option here, which was so PC means pericynthian. That means the closest approach to the moon. So an additional burn 2 hours after pericynthian would shorten that return time by 10 hours. And that only took another 262 meters per second, and it would bring them down in the Pacific. They could have shortened this even further by getting rid of the service module. But there was a discussion about that, and it was decided that that was an unnecessary risk. The service module by this point wasn't really doing anything useful in terms of the equipment that it contained, but what it was doing was acting as a protective cover for the re-entry system, for the heat shield that was fitted to the base of the command module. And that heat shield had to be in top condition in order for it to perform properly and protect the spacecraft from that re-entry. So nobody knew what was going to happen if they jettisoned the service module and that heat shield was exposed to the deep cold of space for so long. So the circumlunar return without the jettisoning of the service module was chosen. So this is a little sequence from the documentary that I worked on. I'm gonna shorten it very much. Here you see the principle of the free return, just in case anyone's not familiar. So you leave the Earth, you enter a parking orbit, you then do a translunar injection burn, which sends the spacecraft to the moon. If you do nothing else, the spacecraft comes back to a very precisely calculated point and lands in the ocean where there is a ship ready to collect you. What happened on the H missions looks very similar. So the spacecraft leaves the Earth on a free return trajectory, but at a point in time it departs to access different regions on the moon. And in the case of the Apollo 13 flight, the failure takes place sometime after the departure from the free return trajectory, and the abort mode that had been chosen, which I've just talked about, is a one which does a little delta V that returns them to the free return trajectory to bring the astronauts back to Earth. So this is the descent propulsion and the service propulsion system. So I show this to some of my astrodynamics and propulsion students. So these are all to scale. So this is a standard engineer, a standard unit of measure. So this is the ascent propulsion. So this is the propulsion system that would bring the astronauts back from the surface, and it was fitted in the upper stage, the ascent stage. This is the DPS, the descent propulsion system, fitted in the first stage, and this is the service propulsion system, which is this much bigger engine that you can see here in this computer graphic, which powers which is the propulsion system for the CSM, the Command and Service Module. So this descent propulsion system is the one which was now going to be used for all of the major propulsive events that took place from that point. And one of the things that really comes through when you look at the reports is just how well prepared NASA were for all contingencies. There was a test during the Apollo 9 program, the Apollo 9 mission, which was the first mission that would fly a functioning lunar module in Earth orbit with the service module, with the Command and Service Module. And one of the activities in that program was a test of an engine burn of the lunar module descent motor while docked to the Command and Service Module. This was seen as being a potentially important thing to be able to do for situations that might arise in future. So this had already been tested and characterized. So at 61 minutes 29 seconds, there was a free return burn performed with the descent propulsion system that resulted in a change of velocity of just 11.5 meters per second. But that allowed the astronauts to come back to that free return trajectory. What's interesting about this is that it was performed with the lunar module primary guidance, navigation, and control system. So in the minutes before shutting down the command module, there'd been a very frantic activity to transfer the coordinates and the attitude knowledge of the spacecraft stored in the command module's computer to the parallel system in the lunar module. And so it was possible to do this burn with the lunar module motor using the lunar module's navigation and control system. And you can see here aspects of that. So this is an inertial platform. So this is the gyro platform that was in the lunar module, and this is the telescope that was used to align or check the alignment of the module using stars and using other sighting techniques that some of you and I do in my own astronomy. Use this perhaps to align your mount. So 2 or 3 stars allows you to get a solution that then allows you to point your mount in any given direction. It's exactly how it worked here. So what was then done was the power was left on, so that navigation system was retaining its memory in time for the next burn. And the next burn was this pericynthian plus 2 hour burn, second burn with the descent propulsion system. That propulsion system, by the way, never intended to perform more than 1 burn. But nevertheless, it was done. They used a sun sighting technique just to check the alignment of the system. They powered the lunar module up. They successfully performed the burn, 262 meters per second, and that shortened the return time to 143 hours, and that shifted the return location from the Indian to the mid-Pacific Ocean. They then had to power down some of the lunar module systems because there wasn't enough battery power to see them through the rest of this rather perilous voyage, and that's going to be significant shortly. So there's an aspect of this that suggests that the timing, if it had to happen at all, the timing was about as good as it could get. The consumables are interesting to look at. So the oxygen, in fact, the oxygen was never a concern. The lunar module was designed to support only 2 astronauts for 45 hours, but it was designed to include 2 depressurization and repressurization cycles. So they had enough oxygen to breathe. There was no danger of the oxygen running out. Where there was a real problem was in electrical power. They'd lost the fuel cells. They only had battery power left. And also water. Water was an issue, not so much for drinking, but because water was used to cool the electronics. And without cooling, the electronics would rapidly overheat. So water was a key concern, and they had to reduce the power consumption in order to keep not just the battery power adequate, but in order to keep the temperatures low, so they didn't use more water than they had access to. And then famously, the CO2 lithium hydroxide canisters that would scrub the air of poisonous CO2 that the astronauts were exhaling. Well, they had plenty of those. The problem was, of course, as we all know, the shape was wrong. So why did I say that the timing was good? Well, the timing was good because if it had happened earlier, then these consumables would have been under much more pressure by the time the spacecraft got back. If it had happened later, then by the standard schedule of tank stirring, this would have happened when Lovell and Hayes were on the lunar surface. What was interesting about this sequence of events was that the anomalous behavior of the tank had a second effect, and that was that they were having to stir it more often. This event happened on the 5th stirring of that tank. 5 stirrings of the tank in the normal timescale would have happened when they were on the surface of the moon. So it's an interesting thing to speculate about. The combination of problems led to a timing that was perhaps the easiest of the timings to the points in the trajectory to recover from, though none of this was easy. So I'm gonna talk very briefly about this because I think it's the part of the story that is most familiar. So there was a master alarm that sounded in the spacecraft, and you'll hear it now. I'm going to move on to 1 minute 20. Oops, Daisy, sorry. So at 1 minute 20, there's a call for master alarm.
Okay, Houston, we just got a mass alarm and an ECS light. I take it the partial pressure CO2 is, yeah, that's what tripped it.
Okay, so that's there's that mother is a reference to them seeing that light coming on again. And what was clear at this point was that the CO2 levels within the spacecraft were becoming dangerously high, and that mother is actually a light that indicates this in the spacecraft. Two more significant points in this sequence.
Jack, we might have to have you rig up the CO2 rig they're talking about.
So that's the decision to make a jury-rigged approach to allow them to use the excuse me, to use the square CO2 scrubbing units from the command module with the cylindrical CO2 scrubbing unit receiver in the lunar module, which we'll look at very briefly on the next slide. And the last thing that I want to just play here is a rather plaintive bit of telemetry at 7 minutes.
Nope, he didn't want it. There she goes, gang. The moon.
So I don't know whether that came through clearly, but that's Lovell saying, "There she goes, gang, the moon." And that's a point that's well reflected in the film. And at that point, the astronauts could see the moon. They knew that they weren't going to be able to get down to the surface, and they'd effectively lost that opportunity. The story that follows is well known. Thanks to a very detailed inventory of flown items on the spacecraft, NASA recorded absolutely everything, every material that was on board. It was possible for a team of people on the ground to come up with a method using the cover of the flight plan, using duct tape, which was flown on every flight, and a whole set of other resources to allow them, as you see here, to connect that square scrubber from the command module into the cylindrical receiver in the lunar module. So that very careful inventorying is a part of the reason why they were able to be retrieved successfully. But this is a failure of systems engineering, because the contractors for the two parts of that flight architecture were different, and nobody thought to consider that maybe unifying the design of those scrubbing cartridges used in the two different parts of the spacecraft was a sensible thing to do. Okay, so having corrected the CO2 problem, they also had to correct their arrival conditions. They'd succeeded in retrieving or returning to the free return trajectory. They knew that they were going to arrive at the Earth, but that's not the whole story. You can't just arrive at the Earth. In order to descend safely to the surface of the Earth, your angle of entry into the atmosphere has to be correct, and the range of acceptable angles was between -5 and -7.5 degrees, with -6.5 degrees being the ideal. Now, one of the things that they realized was that after the second burn, their angle of entry was very close. So they'd achieved -7.1 degrees, but it was at that value at too high an altitude. So they needed a mid-course correction. And mid-course correction 5 is the one that was used to do this, but it was brought forward from the normal mission plan for a particular reason, and that reason relates to the lunar module descent propulsion system. So remember that descent propulsion system was not designed to do more than one burn, and it was designed to end its useful life on the surface of the moon. The propellants were delivered to the motor using not pumps, but using pressure from a helium tank. before the motor was used in the normal flight sequence, that tank was kept cold. But once the motor had been used, the tank was warming up all the time. But once the motor had been used, heat from the motor would be transmitted by conduction deeper into the architecture, and the rate of warming in that helium tank would increase to the point where the tank would threaten to burst. But that was okay, because at this point in the mission, normally the lunar module was on the surface, that motor wouldn't be used anymore. And so there was a very elegant, simple solution, which was to fit the tank, the helium tank, with a burst disc. And that burst disc was designed to rupture when the pressure got to a particular level, to safely vent the tank, rather than the tank rupturing violently, which could cause a risk. That's how it worked in normal missions. But in the case of Apollo 13, this was a problem, because they had to do all of the maneuvers that they required the DPS for before the burst disc ruptured. And so this is why, if I just step back, this is why they brought forward that mid-course correction maneuver from 118 hours to 104 hours, so they could be sure they could do it before the helium disc burst. Before the helium burst disc failed. Because once that helium burst disc has failed, there's no pressure in the system, and there's no propellant can be delivered to the propulsion system. So they had to do this burn with manual guidance. They'd shut down the lunar module guidance system. They'd shut as much down as they could to save power for recharging the command module batteries from the lunar module in preparation for re-entry. So they had to do this manually. They had to do a manual star alignment. And this is where a rather interesting kind of accident in Apollo 8 became very significant. So in Apollo 8, there was an incident in which Jim Lovell mistakenly entered a character into the flight computer. And that meant that in Apollo 8, there was a need to realign the spacecraft. Now, it wasn't a threat, because they had the benefit of the onboard guidance and navigation system. They could easily have brought it back into alignment. However, there was a manual way of doing this, and Jim Lovell decided that it would be a good opportunity to test that manual way. Now, it's a peculiar thing for NASA to have developed. It's a technique which was developed because one of the flight engineers had a thought one day, which is, we do this manual alignment using stars, but what if you can't see stars? And the initial response to that is, why would you not be able to see stars? You're in space, there's no cloud, there's no rain, you can always see stars. This is a good example. So this is telemetry ground loop from Apollo 13, and you now start to understand why being able to align without seeing stars became not just interesting, but critical.
And now we want to ask you a question about alignments and so forth. We wanted to know if you can see any stars out of the AOT. We also wanted to know if you could use the service module to cast a shadow on the LEM windows and then look out the windows to see stars for P51, COAS alignment.
So that's asking Lovell if he can see stars through the Apollo optical telescope, because if you can see stars, then we can use those to align. And the response that comes back from Lovell is as follows.
Another problem right now, Jack, I'm looking out the right window, and it's pretty dark out that window, but there are about 1,000 or so false stars out here from leftover from some of the debris. It's hard to discern what's real and not real.
So there's the problem. So they're in space, there's no cloud, surrounded by thousands and thousands of visible stars, but they're also surrounded by thousands of particles that have been released from the spacecraft, fragments of debris that are creating false stars. And that meant that it was not possible to use this stellar alignment process for the course correction. So what happened instead was that Lovell had an opportunity to put into practice the test that he'd done on Apollo 8. And in that case, the way that they did it was to use the cusps of the Earth's terminator. So they could see the Earth's the terminator, the division between the bright and the dark side. The cusps are the points. So we're used to talking about the cusps of the moon. So the cusps of the Earth were visible. These are graduations in the window of the lunar module, and those graduations were there to help gauge the attitude of the spacecraft with respect to external references. So they placed the illuminated part of the Earth in the lunar module reticle. They then constrained the spacecraft such that the sun was in the upper portion of the Apollo optical telescope, and used timing, so dead reckoning, using a watch to align the spacecraft and then time the burn of the descent propulsion system at MCC5. So that was an absolute triumph, using procedures that had been invented for no real apparent likely eventuality, but which turned out to be absolutely critical. So at this point, they're in good shape. They're heading back to the Earth. They've got a good alignment. They're going to enter the Earth's atmosphere at the right angle. Conditions by this time were utterly miserable. They'd powered down the systems. There was no waste heat from electronics to keep the interior of the spacecraft warm. It was around about 3 degrees inside, and there was significant condensation, and this was a problem. There were water droplets on the walls, and behind the panels where all of the electrical connectors were, it was likely to be the same. Another issue that they had was an inability to dump waste. So they were, this is a quote from Lovell, that they were looking for all sorts of bags and containers to put urine and feces in, because they couldn't dump it over the side. It would modify the trajectory of the spacecraft. So they were getting pretty close to running out of places to put things by the end of the mission. Just coming back to that cold, damp atmosphere. This is the fact that there was no electrical shorting is a direct consequence of the remedial work and the changes to the design that were implemented after the Apollo 1 tragedy. That's a different talk, but one of the changes that was made as a result of the Apollo 1 fire was a change to the way that wires were insulated and potted, protected from whatever atmosphere is inside the spacecraft. And had those wires not been insulated in the way that they were post Apollo 1, there was a very high chance that there would be a short. So coming to almost to the end of this story, then at 138 minutes, the service module was separated from the lunar module. This is a simulation. And I'm just going to wind it back. It froze a little bit there, so we're going to rerun that simulation. Let me start it again. Okay, I'm gonna move to a different view. So this is a view which was captured by the astronauts at the point of service module separation.
We copied that report from Jim Lovell of service module separation at 138 hours, 2 minutes, 8 seconds.
And there's one whole side of that spacecraft missing.
Is that right?
Right by the high gate antenna, the whole panel is blown out, almost from the base to the engine.
Copy that.
And it looks like it got to the SDS cell too. It's really a mess.
So that gives you an idea of the damage that was sustained, and close analysis of that footage also suggests that the service module propulsion system had actually sustained damage to the engine bell, and that, if that had been used in the recovery activities, that would have undoubtedly resulted in a very significant off-axis thrust at the very least. And that justifies Krantz's decision to go with the longer but safer return abort mode. So we're pretty much there, and at the point at which the lunar module was jettisoned, the resources were pretty good. So we said that oxygen wasn't a problem. There was lifetime to 146 hours after launch for the electrical power system. There were 28 pounds of water left, so that would have taken them to 147 hours, and there were 37 hours of lithium hydroxide oxygen CO2 scrubbing canisters left. So they were in excellent shape by the time they returned to the Earth at about 141 hours, or 142 hours. Sorry. So we're pretty much there. This is the footage from the return. So this is from the recovery vehicle.
Standing by for confirmation of main chutes.
Odyssey Houston, we show you on the mains. It really looks great.
And that's the call that everybody was hoping for. And we just leave with a few nice images of the return. So that I think covers the sort of the key aspects of the flight, some of which are familiar, I'm sure. Some hopefully maybe new or to you, or at least giving you a new angle. And just a few final thoughts. I think, as I said earlier, the biggest risk to the astronauts during that whole mission, in retrospect, was the event at 5 minutes into the launch, the pogo from the propulsion system. That oxygen tank failure was completely avoidable. It was brought about through a series of failures in process and systems engineering approach. The failure of the procedures during the tank removal may have led to a problem, but the requirement specifications for the thermostats during the detanking in the detanking system almost certainly contributed to that. But it could have been worse had the timing been different, had the panels not blown to reduce the pressure in the service module, command module assembly. And ultimately, having criticized some of the aspects of the systems engineering process, without a doubt, the successful outcome is really down to the discipline and the preparedness of the teams who were working those problems both on the ground and in the space segment. So it was an accident, but they didn't get back by accident. They got back because of this enormous level of discipline and preparedness on the part of the teams working. And so that is where I'm going to end. I think I've well and truly blown my time budget, so my apologies for that. I'm happy to stay around and answer any questions, and I've just put a few references at the end that you may find interesting to get some further information from. So thank you very much. If anybody is still there, I'm happy to answer questions.
There's plenty of us still here. Chris is going to come over now, I believe, and we've got a few questions come in, and he'll ask them over to you.
Sure.
Hi, Nigel. thank you so much for that. That was, as we mentioned before, that was absolutely right up my street, which is part of the reason why I asked if you would do the presentation for us. There'll be a vote of thanks later on, but before we go on, I do have a few questions. There's about 7 in the box at the moment.
Sure.
So if anybody else has any, then please drop them in the Q&A box. I have a couple myself, which slightly selfishly I'll start off with first. How much, notwithstanding the thing that you mentioned about the electrical insulation, how much did NASA take from the Apollo 1 fire and then use in the resolution of the Apollo 13, accident stroke emergency, and how much was their protocol and their techniques changed after the fire that helped to get the crews back?
So the Apollo 1 accident was something that really transformed the design of the spacecraft. I think the big issue with the Apollo 1 as far as Apollo 13 is concerned is the way that they designed their electronics and some of the materials that were used in that system. So I think in the overall analysis, I think that's the principal legacy for this particular issue. But of course, Apollo 1 led to a whole set of different design modifications for the overall Apollo architecture, including changing the way that the access hatch worked, changing the policy on the partial pressure of oxygen which remained inside the cabin, and so on. So I think, I think really, yes, it's the design and preparation of the electrical subsystem, and in principle the finishing of the wiring that was the main issue, the main contributor for this particular incident.
Sweet, thank you. I did have a question about the helium disk, but that was actually well covered in the presentation. I do have one question though. When we talked about the free return trajectory versus direct abort, had the SPS not been damaged, how were they going to do that? Were they just literally going to pitch up 180 and then just do a burn, or were they going to fly in effect like a turn? And how much of that would have had an effect on the IMU? And would there have been any issues with the guidance platform toppling?
No, so gimbal lock is a major issue with the kind of guidance platform that the Apollo architecture flew, and I didn't mention gimbal lock, but there was during, I think it was MCC 5, there was a concern over gimbal lock, and there's some telemetry, some call outs where you can hear. I think it's Hayes telling Lovell that he's getting close to gimbal lock. So let me just go to the relevant abort slide. Let's just skip through. It's about 300 slides in, I think. So
okay, GNC.
No, we don't want to hear that again. Good Lord. Yeah, there it is. Okay. So the abort maneuver is here. This is the directory that the spacecraft is taking at that point, and what we can see is that there are a couple of different versions of that abort maneuver. One includes a very significant retrograde component. So if we think the spacecraft is moving in this direction, you can see the arrows heading out towards the moon. For the spacecraft to enter this dashed line, that is a high delta V maneuver, which has a very significant burn in the retrograde direction, so forcing the spacecraft directly along this line, but also an almost equally significant perpendicular burn. So what they're doing is they're swinging the vector from this direction around to this direction. The other approach that would be taken, so there were two versions of this. One is to minimize time, and the other one is to minimize fuel. So this is the fuel minimized approach. And what you can see here is that the burn is prograde. So if you think that the line for this fuel critical return the initial vector is in this direction, and then the gravity of the Earth is causing the trajectory to swing around this way. So the spacecraft gets a bit closer, or a little bit further away from the Earth, sorry, a bit closer to the moon, and then swings around under gravity. So that's a lower delta V, and it's performed with effectively a small delta V in the direction perpendicular to the trajectory. Does that make sense?
Yes, that's fine. Yeah, absolutely understand that. Cool. Excellent. Thank you very much. Right, so now on to the Q&A. So Richard's put a couple in. First one is, do you think future space flights will have the same level of excitement and enthusiasm from the general public as the Apollo series of space launches?
Ah, that's a really good one. Do you know, I've thought about this a lot. So I don't know what it's like for everyone else, but when I think of Apollo, there's just a feeling that I get, and I don't know whether it's because it happened around the time that I was born, and it kind of had a big effect on my life, or whether it's because it was the first. There can only be one first, and it's the first time that we'd explored another world. So my feeling is, I hope I live to see the first humans set foot on Mars. But sitting here today, I don't think that will have as big an impact on me as I think the lunar landings had. But when I talk to my students, for my students, Apollo is ancient history, and they talk about landing on Mars, I think, with the same kind of magic that I think about the Apollo program. So I think it's really difficult for my generation, possibly not. I think for the current and future generations, humans landing on another planet and possibly setting up, a permanent base, becoming a 2-planet civilization. I would like to think that inspiration and that magic is still there.
I guess that's only just a matter of time and money. But on a similar vein, and I know we talked about Artemis a little earlier on before the main event, but Pete's asked, when do you think we'll see humans on the moon again?
So the Artemis program is proceeding at pace. So we're looking at potentially the first circumlunar voyages within, I think I should have brushed this up before I started, but I think within the next 24 to 36 months that's planned. Where are we now? It's 2023. I think we are going to see a return of humans to the surface of the moon by the end of the decade. And in fact, if you just allow me, I'll just look up the current projections and find out. But I think it's going to happen soon. The major investments have now been made. The astronaut selection that ESA have just gone through does contain the first European astronauts that will set foot on the moon. We don't know which ones they are, but they're there.
They've just announced the first Artemis crew, and I've talked about the first female to go to the moon and the first Black American going to the moon as well. So, or American of color, I think, is the way that was actually described. But more questions. Rich has got another one in. Were a single type of scrubbing module used in later missions?
That's a brilliant question, and I'm going to tell you that I don't know. I don't think they were, because by that point the lunar modules were effectively built. Do you know, nobody's ever asked me that, and I never thought to look it up. So good question. I'm going to look it up.
Thank you very much. Ray has asked, why did the astronauts not get into their EVA suits to at least mitigate some of the cold?
So EVA suits are cumbersome. They were stowed within the command module, and the amount of insulation that they would have had. There was no power. See, the EVA suits, they get their performant because of power. They didn't have the power in order to run those within the spacecraft environment. So the having to get into the lunar module with 3 astronauts with EVA suits on also is a real challenge. The lunar module was cramped already, and it was only it was designed to handle 2 astronauts with EVA suits. 3 astronauts with EVA suits would have just compounded the problem.
Cool. Yeah, that probably would have just left Jack Swagger in his flight suit whilst the other 2 wore their EVA suits, I reckon. So Pete has asked what happened to the command module and the lunar module after separation. Did they burn up, or are they still around somewhere in space?
Yeah, so both the service module and the lunar module were re-entered. That is the case.
I presume they burnt up on re-entry.
Absolutely, yeah. So if you think about what was happening there, the MCC5 burn was the burn that corrected the trajectory so that the spacecraft would enter the atmosphere at the right point in time, and that burn was done with the lunar module and the service module attached. So when those elements were detached, there's a slow drift away from the command module, but essentially the lunar module and the service module are sharing the general trajectory. So that tells you that they would have later re-entered.
Okay, cool. Last question, and then we've just got a comment. So Rich has put another question in. Is the prior to CIL section therefore the most dangerous bit, as until this happens, any abort procedures cannot be adopted?
Prior to COI,
I think he probably means COI actually, but
okay, no. So there's a set. There are a whole set of other abort opportunities that include the use of, for example, the escape tower during the early phases of the mission, or in fact flying an arc, sort of separating from the stack and flying an arc in the later phase of the mission before COI. So those abort options, they cover the entire flight plan. They're pretty comprehensive.
Copied. And then the last, it's not a question actually, it's from David Patterson. In fact, he even starts off with the words "not a question," but it was interesting to hear the raw recordings around the time of the accident. All the recordings I've heard previously went almost instantly from the tank stir to "we've had a problem. Thank you for an interesting talk," which I think is also the same in the film as well. So I reckon 2 minutes of not much happening wouldn't have been particularly viewer friendly, but yeah, so all the previous recordings, it sounds like it's almost instantaneous. So I agree with David. It was interesting to hear the fact that actually there was a considerable period of time after the original stir before anything actually happened.
That's right. Yeah, and I find it fascinating that you can hear the first thing you hear is just the fact that the antenna has been pushed off beam, and that's the signature of this massive disruption that's about to take place.
Thank you so much. Excellent talk. I will hand you over to Pete/Tim for the vote of thanks. But Nigel, thank you on my behalf. Thank you so much for that. It was fascinating.
Real pleasure. Thank you very much.
Thanks, Chris. Wow. I mean, that has been absolutely fascinating talk, Nigel. Actually, it's been a bit of a like a time machine for me. I was thinking back when you were saying that you born just at that time, and for me, I was in my early teenage years. Dates me a bit, and it brought back memories of something I used to do for the Apollo missions, starting with Apollo 8. I bought a pack which had been designed. It had like cardboard cutouts of the command module and all that kind of thing, and a chart to show what the path was going to be for Apollo 8, and of course you saw this on television in those days. Patrick Moore and James Burke were the presenters, and I was quite taken with the fact that they had all this fancy tech. Back then it seemed high tech. Today it's pretty pretty poor tech, but back then it was fascinating seeing them with models of the spacecraft and that kind of thing. And I kind of thought, well, I'll simulate it for the family. So I laid out the orbit, and I used to keep track. I had a stopwatch once it had launched to keep track of the time. And that was great fun until, of course, Apollo 13, it didn't quite fit into that scheme of things. And of course, I spent, like a lot of people, most of my time riveted to the television, and absolutely fascinated. I hadn't realized that you mentioned there the navigation reverting to the cusps, the Earth's cusps. What that reminded me was that, and it probably applies to some extent still today, that actually having some of that basic knowledge can quite often get you out of real problems, even today. And as we become more and more reliant on technology and the internet and so on, sometimes just having that basic knowledge is important.
Absolutely, without a doubt. So when I'm teaching my students, there's an increasing reliance on software and black boxes, and you can do things with those techniques that are very difficult to do manually, but always try and go back to first principles and do it on paper and make sure that it looks sensible.
And one of the things that it sort of helped fuel an interest in for me, which was quite sort of a niche interest, was in positional astronomy, celestial mechanics, astrometry, which I really got into as I went through my teenage years. And when I realised, of course, your connection with Leicester, it brought back another memory, because when I was applying for universities, I had set my heart from an early age on studying astronomy. And by the time I came to filling in the UCAS forms back in those days, Leicester was one of the universities I applied for, and I have to say that I was really excited when I got the offer of an interview. I lived in South London, so getting to Leicester for the day was quite a trek for me, but it was great fun, particularly as I was young, and parents were allowing me the freedom to go on public transport, go all the way up to Leicester, and I had a great time, and I met some really nice people. And it sounded really interesting. Had a look around all over the place, and the only thing that put me off, dare I say it, I'm sure it's improved since then, was the accommodation, believe it or not. And I came back, what do you think about it? What do you think, Tim? And I said, well, it was very nice, but it's a really nice people. I don't think much of the accommodation. So, but I got an offer. I think it was something like an A, a D, and an E, something like that. Anyway, but I got offers from other universities, and the tipping point for me, I have to say, and this is no disrespect to Leicester either then or now, was that all their courses were physics-based, physics with astronomy, physics with astrophysics. I think now it's still the case, physics with science. And I totally got that. But I wanted a course that covered astrometry, celestial mechanics, spherical trigonometry, these sorts of things. And so I ended up opting for St Andrews, who had a lot of those topics in the course. Right. But I've always remembered Leicester with my one visit to Leicester with great interest. Of course, back then the Space Centre and so on was, it might have been in somebody's mind, but it certainly wasn't in the forefront of things that it is today. So maybe sometime I can manage to go and visit that. It'd be lovely to do.
Drop me a line. A line. You'd be very welcome.
Well, that would be great. And likewise, it's lovely to have you online here. But maybe one day you can come up and see what attracted George to come back so often, not just his friends and his family, but the area. And I like Howie and others, I always used to look forward to, because he usually came up and he would give a talk. Sometimes it would be to business people, sometimes it would be to schools and so on. And I actually dug out the other day a notebook that I was having trouble keeping up writing the notes, but I've still got them. And I remember going up to him and asking him some questions afterwards. He was a great chap. And you've done him proud by giving us such a fantastic and detailed talk and teaching us things which, certainly a lot of those things I was totally unaware of. So thank you so much for that. And by way of our appreciation, I have here a Sigma, inscribed Sigma crystal glass, which I'm not sure what your tipple is, but you could put orange juice in it if you want, but maybe you want something a little bit stronger, particularly after tonight's talk. But can I thank you so much for giving the talk. This comes with our very greatest thanks for that, and hope to see you here sometime if you're ever in the area, or maybe come back in a few years' time and tell us about how Juice has been getting on. But in the meantime, Rich will be in touch to find the best way to get that glass to you.
So kind. I really appreciate that. Thank you very much, and thank you for those very kind words. I would love to think that I am 1% of what George was, but it's really nice that you've given me this opportunity to have tonight in his in his memory and honor. So I really thank you.
Well, thank you again. Thank you so much, and I'll hand back now to Pete.
Thank you very much, Tim. And yeah, Nigel, thank you so much as well for coming up. That was a fantastic talk. Really enjoyed it, and with the comments coming through, you can see the audience did as well. So, but yeah, I will double up what you said, Tim. We'll definitely get you back, and we'll have to get you up here. We'll have to do a special weekend or something and get a couple of people up from Leicester. I think that's be a plan for the future. How does that sound?
That'd be amazing. Thank you.
No problem. Thank you so very much. Right, so just as I say, we're not going to have a second half tonight, which is quite good. We're on time as we normally finish around 9:30. Hope everyone enjoyed the meeting. So it just leaves me to thank everyone who's helped it to come together. Obviously, Chris, Rich, and Tim there. Rich is still over on YouTube. I'll bring him back in a little while. As I say, Chris, we're doing the questions. Tim, for the vote of thanks. All your good selves for coming along and making it such a good evening for such a special occasion marking George's memory. Our next meeting is on February the 2nd, and that'll be at Lambride. That's our AGM. Don't be put off because it's an AGM. We're hoping to do a bit of solar observing, but obviously the weather gods are going to probably scupple that one again, but we'll see what happens. And also we'll have a buffet like we did last year. Okay, so it's going to be AGM and what we call the soak. For those who don't know what the soak is, it stands for Solar Observing a Kitchen Event. So we get the kitchen going and get some food coming out of it. Okay, let's say hopefully get the solar telescopes out as well. Visitors are always welcome to our meetings, so if you want to come along, please just do come along. We meet at the Lambride Community Centre, and as usual, first Friday of the month, which is the 2nd of June, that's at 7:30. Doors open at 7 with the kettle on, ready for a cup of tea before we start. So with that, Nigel, thank you very much. And to say everyone else, thank you very much for being here and doing what we do. And I will say good night and take care, everybody. Good night now.